All right, everybody, we are on to video 4-2, constant acceleration. Last two videos, the lead-up videos, the starting off videos for chapter 4 had to do with constant velocity. And when I say constant velocity, I want you to hear, when I say the words constant velocity, I want you to hear the phrase, the words zero acceleration. Put them in a nice little floaty cloud up here. Okay. Constant velocity means zero acceleration. Now we're talking about constant acceleration, not constant velocity. Now, but we're now doing it, of course, in 2 dimensions. But let's revisit our formulas from one-dimensional constant acceleration motion. They are your friends. They are my friends, the equations of motion. There they are, in one dimension. Let's give it up for them, right? Yay, we've all seen them, we've all worked with them. You might not like them. You'll like them eventually. Okay? Acquired taste. But there they are. Nothing new to see here. Right? We have applied these in the x direction. Our racing cars. Right? Or not racing cars, just cars moving in the x direction. Maybe a cheetah running in the x direction. We've applied them in the vertical direction, dropping balls, etc. Dropping sandbags out of hot air balloons, whatever. We've applied them in the horizontal direction and in the vertical direction. Now we're going to apply them in two dimensions at once, but believe me, it's not going to be as complicated as you think. There's a simplifying situation that comes up. But before we get to the simplifying situation, all I'm going to say is this. This set of equations applies in both dimensions independently. These equations apply in both dimensions independently. Equations of motion equations of motion. And I'll tell you what I mean by independently later. Okay, well, I'll be very particular about that. Equations of motion apply in both dimensions x and y independent. Very hard to write when you're up close. So, independently. I think I spelled that correctly. Okay, let's be independent together. Remember that from Let's Be Independent Together from Rudolph, Red-Nosed Reindeer. Okay, so these are going to apply in both x and y. But in order to do that, we have to keep some bookkeeping. Right? There's going to be some bookkeeping work because we just can't call both directions x because one's x and one's y. Right? We can't do that. We have to be careful about bookkeeping, keeping the two separate, keep them separated. Okay? So we got to do that, and we do that by using subscripts. So I'm going to add some subscripts to this. Okay? V sub x, that is the velocity in the x direction, is v naught x plus axt. Why did I do that? Why did I just pick v naught, and a? I just keep going, then I'll ask you that question. V naught x, again, ax here, vx here, v naught x there, and a sub x there. Why did I add, everywhere I saw an A or a V, I added an X? Okay, to indicate that this refers to the X direction. Why did I do that? For V and A. Why did I do that? Because, I'll tell you why. Because V and A are vectors, and they have X parts and they have Y parts. Just like the raptor problem, the raptor snack, the previous video. The velocity was down and to the right. It had a positive X component and a negative Y component. It had an X part and a Y part. You got to keep those parts separated. So when you see V naught X, this means the X part of V naught, which is a vector. This means the X part of the acceleration, which is a vector. Okay? It simply is a way to separate, to make sure that all these three equations now are our three equations of motion for the X dimension. And we can write similar ones for the Y. I'll do that now. V equals V naught plus AT. Y equals Y naught plus V naught. I'm going to add the subscripts in a second if you're wondering why I'm not doing it yet. Plus 1/2 AT squared. Notice T doesn't have a subscript X or Y, right? Because T is not a vector. Doesn't have an X part and a Y part times this time. No subscripts on that. And finally, V squared equals V naught squared plus 2AY minus Y naught. And so we have subscripts here also. V sub Y, V naught Y, AY, V naught Y, AY, VY, V naught Y, AY. These are our three equations of motion for the Y direction. And there's only one quantity that connects them. Right? They are independent, yes. The motions are independent. Again, I'll say what that means. I'll see a minute later on. But there's only one variable that shows up in both sets, and that is the time. The time connects them. That's the only thing that connects them. Other than that, they are completely, absolutely separate from each other. So basically all I've done so far in this first 7.5 minutes is to say that the equations of motion that we've already been using, when you go from 1 to 2 dimensions, we now have to worry about 2 sets of them. That sounds complicated, and it is. Okay? But all we've done here is to do some bookkeeping, some X's and Y subscripts, that's all. And also to call this, for example, Y instead of X, the position. We can't call them both X. So there's a lot of applications for this, but there's one application that stands out far and above in importance above all others, and that's all we're going to consider in this chapter. There's only one application of this. So there's many applications. They are legion. But there's only one we're going to deal with, and that's an application known as projectile motion. Actually, I want to put this further up here. Projectile motion. That sounds like fun, doesn't it? Too bad we're not in lab, because we get to actually in physics lab we actually get to like throw marbles through the air and stuff. Projectile motion. And projectile motion is really any time an object is flying through the air, whether it's a baseball or it's a penny that you dropped from a building or anything like that. We've kind of done some projectile motion already when we talked about dropping balls. But projectile motion is really a two-dimensional thing, so those one-dimensional cases really are not called projectile motion. Projectile motion is a special case of free fall. Okay? Some free fall is not projectile motion, like if you just drop a ball. Okay? You don't really call that projectile motion. But it is free fall. Projectile motion is a special case of free fall. Let me tell you what projectile motion is. Okay, there's basically number one, you ignore air resistance. This is nothing new. You just ignore it. We're just going to forget about it. It's real. It happens, and we might deal with it later on in some later chapters, but not here. Number 2, the acceleration in the y direction is minus g. So everywhere you see an a sub y here, we're going to put in a minus g. Okay, so minus g is going to go here, and here, and here. We can simply substitute in minus g everywhere we see an a sub y. In the third, even better. I've told you how much I love zeros. I love them. I can't get enough of them. A sub x is 0. In projectile motion, there is no acceleration in the x direction. This is not obvious, but it is true. Okay, I'll say more words about this later. Right now I'm just trying to set up the math a little bit for us. Okay? So what I want to do now is to rewrite these, okay, for projectile motion. Everywhere I have an AY substituting in a minus G, everywhere I have an A sub X calling it 0. This one is actually just phenomenal because look what happens. This goes to 0. This goes to 0. This goes to 0. Everything becomes super duper simple. So now let me rewrite these, okay, for projectile motion, which is the only application of these equations we're going to be dealing with. And I'm going to rewrite them simply by erasing them here and putting in the right value. So this term just goes away, poof, like that. I love it, love it, love it, love it when terms go away. Makes my heart happy. This term, 1/2 ax squared, goes away because ax is 0 for projectile motion. Another celebration, another good time, another party. And this whole honker term at the end here also goes away. Things are looking up, huh? A lot simpler. Now let's look down here at y. Everywhere there's an a sub y, we're going to stick in a negative g. So this term here, a sub yt, becomes minus gt. Yes, we're adding a negative number. So p naught y minus gt. This term here, a sub y, poof, becomes negative g. I'll pull the negative sign out in front. Simpler that way. And finally, the third equation in the y direction. The last term, also I'm going to pull there's a g in it, so I'm going to pull the negative sign out front. It's minus 2g y minus y naught. Okay. These are the equations of projectile motion. Okay. And they are basically our equations of motion that we have known and loved all through chapter 2 in 2 dimensions and simplified for this particular application, projectile motion. Okay? So there's fewer subscripts now, right? But there's still, you still see some pink subscripts floating around. But they're all attached to the V's. The only subscripts you see here are attached to the V's, not to the accelerations anymore, because we have substituted in these values for a sub y and a sub x. Next up, let me check to make sure. Yes, we have an example. We do have an example coming up for projectile motion. In fact, even better, we have 2.